about this job and going to this colloquium series every week to meet these senior people who have done all this amazing work, and you think, man, I hope in 10 years I've done that much. Now I get to introduce somebody who is younger than me, and I think, man, I hope in 10 years I've done as much as Richard has. So it's my great pleasure to introduce Richard Socher, who's finishing his PhD at Stanford with Chris Manning and Andrew Ng, and he has single-handedly revolutionized natural language processing with deep learning, and I think that's a fair statement to make, so take it away.
Well, thank you very much for the kind introduction. I'd love to read those critiques. All right, well, thanks everyone for coming. I want to talk to you today about recursive deep learning modeling semantic compositionality. And this is joint work with John Bauer, Alex Perligan, Jean Wu, and my two advisors, Chris and Andrew. So the first question that we should ask ourselves is, why should we be interested in the topic of semantic compositionality in the first place, and why should we use recursive neural networks or recursive deep learning techniques for modeling compositionality? In order to answer that question, I want to first take a step back and look at the first three projects that I did in my PhD and sort of motivate what led me to this line of research. In the first project, I used directed graphical models to try to model how people memorize lists of words. And in order to make inference tractable in these kinds of models, we had to make a lot of independence assumptions that were quite unrealistic, both cognitively about people's brains, but also how semantics emerge from natural text. In the second project, I used kernelized canonical correlation analysis to label segments of images. And while I would love to say how this model was so important and it really helped push the state of the art, really in order to make the model do anything useful, I spent almost half the time of that project on designing the features on both the text side and the vision side. And similarly, in the third project, where it was officially about clustering, I actually had spent quite some time trying to describe the documents or images first in a certain kind of feature space, and then I could run these interesting clustering algorithms that the paper was actually about. And so this leads us to sort of, in summary, to two common shortcomings in both natural language processing research and machine learning research, which is that the first one, we're making a lot of simplifying independence assumptions about both language and visual structure. The first one that is very commonly used is the bag of words assumption, that the order of words doesn't matter, which is of course crazy because if Mary loves John or John loves Mary, that's a huge difference to both parties involved. And one way of fixing that problem is by just looking at local fixed-size feature windows, where around every word that I want to, for instance, classify in terms of part of speech tags or named entity tags, I look at just the features around that word. And that helps us to sort of get a fixed input vector, and it seems like once we have a fixed input vector, we can do a lot of cool things in terms of classification. And basically, that leads us to the second problem, that the data representation and the features can in some cases be more important than the actual learning algorithm. And that seems to be true especially for supervised models. And so in natural language processing, we spent a long time trying to come up with better and better features that help us sort of tame the beast of natural language. We work a lot in parsing. In fact, people don't even consider parsing anymore as like a feature. It's just its own research area. But really, eventually, what we usually care about for downstream tasks is like actual meaning of language or things like machine translation. So parsing by itself became a field, and for some people, a means to an end. But really, it should be a feature. It should be seen as a feature to try to describe language. And we work on named entity tags, and character engrams have been shown to be useful features. We spent a long time creating hierarchies like WordNet to then plug those things into other semantic components into larger systems. And so basically, when we work on these kinds of problems in current NLP systems, we create quite fragile systems, because a lot of the features that we use, even those that come out of those systems, are quite sparse. So for instance, if I have the sentence here, my dog also eats oranges, we parse it properly as an NP here, the oranges, but once I ask the parser to parse the sentence, my dog also eats bananas, I get this crazy sentential complement here of bananas being first a noun phrase, and then an adjective phrase, and then a whole sentence, which is, really weird. And the reason why that happens is there's one example in the Wall Street Journal of going bananas, and going crazy. And basically the model was not able to sort of realize that still bananas and oranges are very similar, and we can sort of make inferences from this example to that example if we don't see going bananas. And so, ideally we would have a better feature representation that will allow us to capture that. And the problem is whenever we engineer features, it's very time intensive, and it's definitely modality, but also often task specific. And it's also hard to parallelize computation when we have very large sparse features, and the current computer architectures don't really work that well and efficiently on very large sparse vectors as much as like shorter dense vectors. So for the first problem, we can basically use deep learning to try to learn the features. The main idea of deep learning is to sort of take a more raw input, whatever you may make of this, for instance pixels or just plain word indices, and try to learn some low-level features that we can then input into our algorithm. And ideally, that will actually be learned jointly, where we have some task, and we basically learn both the features and the task prediction in one joint model. This has worked really great for what I would say are fixed input sizes. So if we have images and we want to classify this, all the images of the same size. And if the image is a little too wide or too high, like vertically, we're just going to resize it to always be exactly the same size. Similarly, it's worked incredibly well for phoneme classification, where we have a fixed window of sound and we want to just classify exactly that window. And also for single word vectors, a lot of exciting sort of semantics have been learned for describing single words. So let's take a deeper look into two of those biggest recent achievements of deep learning. And the first one, for speech, for instance, we see that the output of a deep neural network and in the speech architectures is in the end still given to a hidden Markov model to make the final prediction of the sequence. And for images and sort of recognition, there are interesting phenomena such as neurons at the highest layer of these networks that are invariant, for instance, to cat faces. So one neuron fires when it mostly sees cat faces. That's amazing, but what we realize here is that neither of these models are capturing hierarchical, compositional, or part structure. Right? These are still sort of given to another learning system, and ideally we would learn both of these things jointly, and not just first learn one component and then another. And maybe if we were to do that and apply these division, then maybe we could realize that these are also all cats, and we would have an actual neuron that is invariant to cats and not just frontal cat faces. So that basically led me to this line of research, which is what I generally call recursive deep learning. And one of the main feats that are sort of interesting that come out of this set of models is that basically the ability to have semantic compositionality, which is the main problem of how meaning representations can be composed from smaller units. Generally, these recursive deep models can represent n-grams for arbitrary n. So, for instance, if you think of the Google n-gram corpus, which collects counts for all of from the entire internet, it goes to like 5 or 6. And after that, you run into huge sparsity problems. So these kinds of models, we can represent n-grams without losing the order of the words for much longer n-grams. We can, in these models, jointly learn feature vectors and the prediction task, which is common to a lot of machine learning algorithms. And I'll show you a couple of examples of how they were useful for tasks in natural language processing. For this talk, I will not go into the computer vision results, but a lot of these kinds of models are also directly applicable to computer vision. All right, so the main outline of this talk will be, I'll give you an introduction of neural networks for parsing. I know that Chris was here about 2 months ago, so I won't go into all the details of our work on parsing, but for those people who haven't been at his talk or it's been too long ago, I'll give a quick refresher on this work, because it kind of leads naturally, once we get these tree structures from parsing, it'll lead naturally to doing more semantic tasks inside these tree structures. Then I will basically explore with you some different, the main component of recursive deep learning, which is the composition function. How do we actually compose the meaning from two smaller units? And there are various ways you can do that. In the second part, I will talk about matrix vector RNNs, and in the third part, I will talk about recursive neural tensor networks. There are basically two ways to modify the composition function in these models, and I'll explain all that, what that means in a bit. So for parsing, let's look first at how phrases are usually represented in both semantic parsing and syntactic parsing. Originally, when we looked at semantic parsing, we basically thought of everything in terms of formal logic and lambda calculus expressions. And these kinds of models are extremely useful for sort of querying fixed knowledge bases where you have a relatively small set of entities and you want to get a very concrete answer. But in semantics, it's much richer than just having concrete questions where you have a very obvious answer in terms of like one number or one set of cities or something like that. For syntactic parsing, what we usually do is we start with some coarse discrete categories like noun phrases, prepositional phrases, and so on. But throughout the last decade or so, we basically found that we get better and better performance with more fine-grained categories. So people try to do lexicalization, so adding a word to every noun phrase, knowing this is not just a noun phrase, but the head of that noun phrase is the word tag. You can also do manual feature engineering of PCOGs, or automatically learn subcategories, such as in the work of Petrov et al., who find sort of 30 to 60 noun phrase categories. Or you can go the discriminative parsing route and come up with a lot of features and train a classifier. I want to talk about an alternative way, which is sort of almost the next step. It extends these ideas of having more and more fine-grained representations to essentially having a continuous representation for a phrase. And a vector of even 50 numbers that is continuous can capture much richer information than just a couple of, saying like, what this is one of 30 specific noun phrases. We already know that single word vectors can capture basically distributional information and can be learned in an unsupervised way. So just as a refresher, in these models, generally, words that have similar meaning have similar vector representations and are closer to each other than to other words. So we would expect the vector of Germany to be closer to the vector of France than to Monday. And usually these vectors are 50 or 100 dimensional, but throughout the talk, I'll just describe them in 2 dimensions for visualization. By the way, if you have any questions, I guess we should be able to figure out. So feel free to ask questions. So, of course, words never appear in isolation. So what if I want to represent the phrase, the country of my birth, or the place where I was born? How should I extend these ideas of single word vector spaces to longer phrases? And basically, our idea is to map phrases also into that same vector space. And there's some interesting questions of like, should we do that? Is that possible? What are we capturing in these vector spaces? But I hope to show you that at least there's some sort of interesting theoretical arguments that if we want, we can take offline. But basically, in terms of performance on the actual task that we care about, it will make sense to do that. And so ideally, we would have a phrase like the country of my birth to be close to generally to countries, but also to another phrase like the place where I was born. So they're roughly similar in syntactic and semantic meaning. All right, so that leads us to the question, how should we actually map phrases into a vector space? And I think the answer should somehow be related to the principle of compositionality, which in our case states that the meaning vector of a sentence is determined by 1, the meaning of its single words. So here we assume for now that the vectors for single words are given. And then 2, the rules that are used to combine these single words. So if I have here this possessive determiner my, and I combine it with birth, then the resulting vector should ideally look a little more like birth, but maybe have latently in one of its dimensions some possessive quality, maybe a singular quality, and so on. And then we're basically having a syntactic structure in which we're composing in a bottom-up fashion longer and longer phrases, and then in the end we have one representation that maps into the vector space. And the neat thing about these methods is that they will jointly model and learn both the compositional vector representations at every node that describe every span in the tree, and also the tree structure itself. All right, so how does it actually work? And I'll just give you a brief overview of the simplest RNN, and then we can move on in later parts of the talk into sort of more complex recursive neural networks. So our basic computational unit is exactly that, a recursive neural network, or in short, RNN. And it basically has two inputs, which are the vector representations that we want to describe jointly. So here, the map had already been composed into one vector, and now we want to combine on and the map. So we give those two inputs as inputs to the neural network, and then there are two outputs. The first one is the semantic representation if the two nodes are merged, and the second one, in the case of parsing, is a score of how plausible it was to merge these two nodes. And this is, one of the things you can do. You can say, like, how plausible is it to merge two nodes. You can also say what sentiment emerges once you merge two phrases or two words and so on. So let's look into the details on one slide here. So basically, what we do is we assume we have two vector representations, C1 and C2, and we just concatenate them. In the case of when everything is two-dimensional, we get here just a 4x1 dimensional vector. And then a neural network is really just, this is like the simplest RNN type of architecture, where we just have a single W matrix here. And we basically, this W matrix maps the two vectors into the same dimensionality as the first, as both of them separately are. So this is a 2x4 matrix that will just map the two vectors back into two-dimensional space. And we add a bias term, and then we apply an element-wise nonlinearity in this case, or one that we usually use, a hyperbolic tanh. Just maps and squishes all the numbers to be between -1 and 1. Once we have this parent vector, we can then use an inner product here, a simple score, to say, all right, this was a plausible merging of two nodes in the tree. This model we introduced at ICML in 2011, and there have been a lot of related sort of recursive architectures in the history, so people have even also applied them to tree structures, but they usually assumed fixed tree structures. So when you have parsing, you just kind of rescore them, and also they would often use binary word vectors, whereas these models are much more intuitive and work much better with continuous word vectors. And there are a couple of other details that are pretty important for making them work that are different. Jordan Pollack also, as early as 1990, had a related model called the recursive auto-associative memory. All right, so this was basically work that we've done in 2011, and it worked reasonably well. We've gotten state-of-the-art on some sentiment analysis and some paraphrase detection tasks, but we were not quite happy because with a single matrix W, you can only do so much. You could, basically capture some phenomena, but for more complex, higher-order compositions, and parsing especially longer sentences, performance wasn't that great. Also, when we tried to, parse a very long sentence, we had to use these matrix vector products for every score, every potential, phrase boundary that we wanted to explore, and that was pretty expensive. And so what we did in it last year at ACL, we basically introduced a combination of PCFGs and what we call syntactically untied recursive neural network. The main idea is that the PCFG is sort of a syntactic system that will allow us to prune very unlikely candidates that you've just never seen in your corpus. And it basically provides this kind of model, discrete syntactic categories, the PCFG does, and then we can condition the composition function, the semantic component, on these discrete categories. So whereas the previous model, we would have the same W here at every node, we now know what the part-of-speech tags are and the non-terminal syntactic categories, capital P1 here and capital P2, and we can use a different W matrix depending on what the part-of-speech tags were. And just to give you an idea of how recursive neural networks in general, and this model in particular, compute a sentence vector representation, I will go through one example here, and then, because I know that several of you have already seen Chris's talk, I'll stop with the parsing work after that. So what we basically do is we go through every possible candidate that the PCFG hasn't already pruned out. So here we have a vector, vectors for the, vectors for cat. We pipe them through a recursive neural network model that uses a specific W that knows, all right, we're now combining determiners with nouns, and then we'll continue and look at every possible candidate, and then we can go up in a bottom-up fashion and basically combine the one with the highest score. So we know here the cat got the highest score 3.1, so we combine those. And now we still don't know if it's plausible to merge the cat phrase now with the verb sat, and so we pipe those vectors again into the model, compute again the candidate representation, and then the score from that. And we can basically build the tree structure in this bottom-up fashion that way. All right, are there any questions so far about this model?
Yeah, I'm not, so, but what is the rationale? Just take the concatenation of the as a vector. Now, I know that you just make linear combinations of the two sets of features. Would that be an implication, or is just for computation of features?
That's a great question. So the question is like, why do we concatenate the vectors? You can actually rewrite the concatenation to, I don't know if you can read that, but you could rewrite the equation of WAB as W1A plus W2B. And what you basically see, you have like a sort of weighted combination of those two. And I'm not going to go into the details because I know Chris talked about that 2 months ago, but basically what we learned is that it learns a soft notion of head word. So if I combine the and cat, it knows that I should probably not weigh the resulting vector representation. I should not weigh the very much when I combine the and cat, so that the cat and a cat look more similar and are still looking more like a noun phrase and less like just some random determiner with something. And similarly, it basically captures sort of a soft notion of what linguists call head words, where certain words matter more in the composition. But you're right in that, one, it's quite limited still to have this kind of composition, and two, it's faster, but three, it actually doesn't work as well. And so what we'll explore in the next two sections are much more powerful composition models that have linguistic motivations also.
So basically, you assume semantics are additive.
We do in this model, but we don't in general. And also, so this is just the inside the neural network, you also then apply nonlinearity. So if two values are very large, you squish them, and the nonlinearity will allow you to have much more complex composition functions than just linear additive functions. All right, so after this slide, I'll basically assume that we have these parse trees given. You can use now the Stanford parser that we published in the core NLP package, which uses this kind of recursive neural network to do parsing. So for the rest of the talk, I will assume that the parse trees are fixed. All right, so now we can actually look at some more interesting tasks. The first one is relation classification, and also some more interesting composition functions that aren't just sort of have this additive function inside the nonlinearity. And basically, what we know from our first couple of papers in this field is that we can sort of learn some compositional vector representations. However, we cannot capture word-specific operational meaning. So, for instance, if I have a word like very or pretty, then maybe what I want is to have pretty be some kind of operator as an adverb that acts on an adjective. So if I say pretty and I combine it with bad, I'm going to get something like pretty bad. And so what you see in these figures here is basically a distribution of 1 to 10-star movie reviews and how often we see the single word or the bigram inside movie reviews on IMDb. And so, pretty is kind of an attenuator. It's, mostly seen in movie reviews with 6 stars, whereas bad by itself, appears mostly in very negative 1-star movie reviews. And we can see that, once you combine the two, you have a very nonlinear relationship here, where, you can't just kind of, add sort of the vector semantics to the. Sorry, my computer just popped up some good things. All right. And similarly, if you look at the distribution of not, how often does not appear in these different movie reviews, and combine that with that, you can also see that not isn't actually purely logical, and that's sort of what we mentioned with how, semantics is more than just discrete logical inferences, because not bad doesn't necessarily become all the way positive, but it's definitely becomes more positive, and it's roughly maximized at 6-star movie reviews. So the question is, how could we model that some words, in especially adverb-adjective combinations, actually are operators on other words? And the answer is with what we call a matrix vector recursive neural network. So this was our general equation before that we used for everything, and what we now use is this kind of equation. So let's step through that. Basically, we assume that every word and phrase will be represented by both a single vector and a matrix. And when we compose the two, we apply the matrix of one to the vector of the other, and vice versa. So now I can say very as an amplifier acts on the vector of good and sort of makes it longer or rotates it slightly into the more positive area of the vector space. And we also actually go back and allow good to modify very. And there are actually some interesting examples where, depending on the adjective, the adverb also acts somewhat differently. But if you're really opposed to that, you could force the model and set some of these matrices to just be the identity. Basically, if both matrices here are set and forced to be at the identity, then you would recover the original model. And of course, this works in the first step when you combine the first two words, but then if you want to combine the resulting phrase again, you need to have, again, a matrix for the resulting phrase. And so basically, we use this equation here to simply compute a matrix for the resulting non-terminal node in the tree. So let's look at a couple of examples here of the matrix vector RNN versus the normal RNN on some unseen adverb-adjective examples. So basically, for the most part, they're quite similar, but you can see that for really tough cases like not, where you really want to shift around the distribution, the normal RNN doesn't have enough power to really change the predicted distribution of appearance in these different reviews. And similarly, here for not awesome, we see that the normal RNN is still very positive, but the MVRN is able to push that down. And unbelievably sad is actually one of the interesting cases that linguists are very excited about. Does anybody have an idea of why unbelievably sad peaks at both 1-star movie reviews and very highly rated movies?
Unbelievably sad that I sat through this movie.
Exactly. So sometimes, like, sort of the performance or the acting or the story, well, the acting was unbelievably sad. In other cases, people love, tearjerker movies like Titanic and so on, and actually like the sad story. We had a question.
Looks like this one is very prone to overchaining, because once you overchain in the lower parts, you keep overchaining when it kind of.
Yeah. So the question was like, this model is very prone to overtraining, which is true. Which is why instead of using the full matrices here for every single word, also blows up the number of parameters. We actually use low-rank approximations to these word matrices to reduce the number of parameters.
So how do you, is there a tuning there?
Yeah, you cross-validate on your def set for the rank. Yeah.
But you're still additive.
Well, you're actually multiplicative, right? So you're multiplicative, then additive, and then you still have nonlinearity on top. So it's much more than additive. And one of the elements of the model is additive, but together they're very much. All right. So I mentioned actually that we're going to do relation classification. It's a little harder to sort of motivate and visualize this, but basically what we wanted to ask here is, can this kind of MVRN learn how the syntactic context actually composes an aggregate meaning of relationships between words, and this particular experiment between certain nouns. So we basically want to classify semantic relationships between pairs of nominals. An example would be, my apartment has a pretty large kitchen. We're given that this is an entity, and we want to learn that they're basically in a component-whole relationship, where E2 is the component and E1 is the whole. So it's sort of, for those of you familiar, similar to semantic role labeling, but it's, you don't necessarily need a verb. And this was a semi-valid task in 2010. And so ideally, we learn the features as part of our model. And so the way we do this is we basically built a single compositional semantics model for the minimal constituent that includes both terms. So if I go up the constituency tree, and as soon as I hit a node from which I can go down to hit the other word, then I take the features, the feature vector representation or the node representation at that node, and I feed that into a classifier. And in this case, the movie showed horse. I want to train that classifier, in our case, a simple logistic regression or softmax classifier, to basically predict that. And this classifier will then propagate its information down through the tree by standard stochastic gradient descent methods during training. And during testing, we're again just given two entities. We go up the tree, find the vector, the node that spans both of them, and then take that as our feature representation. So these are some examples of what this model actually does. There are like 10 different relationships, and each of them had a different ordering. So E1 and E2 is different to E1 and E2, E1. So if we have roadside attractions are frequently advertised with billboards to attract tourists, the model correctly classified, okay, this was a message topic relationship with the entities in this order. And then learned that the features for this task together. However, for the semi-val challenge, we had some pretty stiff competition. So we had some people, use some standard methods and used a couple of good features. But there's one team in particular which won the competition and used basically every possible feature that you could throw at that problem. So they used part-of-speech tags. They looked at WordNet features. They, tuned, manually found like good prefixes and other morphological features of the different words. They also ran dependency parse features, 11 classes. They looked at prop bank. They used FrameNet to extract more features, numlex plus. They looked at all of the billions of Google n-grams as an additional source of features. They ran paraphrase system on top of it. And they ran text runner, which actually solves one of the tasks. There's an instrument agency, which actually is given by text runner. So it's like, pretty tough to beat that. And when we started training our model, and basically we got to 70.9, and then the paper deadline came around, and we're like, it would be much better if we could have state-of-the-art in our abstract as an n-gram. And so we got desperate, and we also added 3 features. Because basically, that data set just wasn't big enough to learn all this semantic knowledge that these things combine. But basically, it was just 3 simple features from one package, part-of-speech tags, WordNet, and some named entity tags. With those 3 features, we're then able to beat their system. We're like, all right, it's enough on this data set. But yeah, so basically, we learned most of the features here. There's some things that the data sets aren't large enough that we can train. And this is actually one of the lessons that we took for the last part of this talk that I want to mention or talk to you about, which is basically sentiment analysis, where we learned that it's not just in the data, not just in the model, but it's also in the data set of how well these models can do. So first, let me motivate why I work on sentiment analysis, because I think there's some people in NLP who kind of think less of it than of parsing, for instance, where there's one really strong data set where everybody has been working on for a long time. I actually think that sentiment analysis is both linguistically very interesting task, but it's also crucial to business intelligence, marketing, stock trading, and so on. And if you think it's kind of insane to do stock trading on sentiment analysis, it's actually already being done. In fact, in 2011, Anne Hathaway starred in a movie, and as soon as the movie got good reviews, the stocks of Berkshire Hathaway went up a significant amount without any other news about Berkshire Hathaway. And so it's clear that it's already being done, and it's also clear that it can still be improved. And I guess in this case, especially with sort of entity disambiguation. All right, so there's sort of the sentiment that the sentiment task by itself is relatively easy. And I think that's partly because for very long documents, you can't reach accuracy in the 90s. And I think it is mostly because there are a lot of easy cases. If you have a very long document and at some point you see the word horrible and then you see another like terrible, it's really hard to bounce back from some of these words. Even if you say it was not horrible, that doesn't really mean it was a good movie, right? And similarly with awesome, even if you negate awesome, it still means it's a pretty positive review. However, for a data set of single sentences and single sentence movie reviews that was introduced by Pang and Lee, the accuracy has never reached above 80% in the last 7 years. And we argue that it's basically because the harder cases that you hit once you go above 80% really require you to actually understand negation, the scope of negation, other sort of trickier semantic effects. And so let me give you 2 examples of this. So the first one is this movie doesn't care about cleverness, wit, or any other kind of intelligent humor. To a bag of words kind of model, you have a lot going for this being a positive sentence, right? You got humor, intelligent, kind, wit, cleverness, care, 6 positive words. But then you just have this one little dozen in front of it, and the whole thing actually becomes really negative. Similarly, here you have a second example. It's not life-affirming, it's vulgar and mean, but I liked it. And for those kinds of examples, you really want to understand that what comes after the but usually sort of pragmatically matters much more than what came before the but. And so, we're not the first people to realize that maybe with some syntactic sugar on top of these kinds of models, we could do better. So the main idea of using sort of syntactic syntax to try to deal with this and try to deal with negation scope and these contrastive conjunctions like but were had by several people. So they use dependency trees or constituency trees and so on. And we actually also had a couple of models. However, there's one problem that even after all these had been published a couple of years ago, bag of words models were still very popular. And the problem was that syntactic models didn't actually outperform these other models by very much, if at all. So if you carefully designed your models and used some bag of words or maybe ideally bigram features, maybe a lexicon or so, you would still do reasonably well. So the question is why haven't they outperformed these much more sophisticated models? And the answer is because we cast the problem in a way that doesn't actually help, help syntactic models. So we would say that this entire sentence was negative, and maybe this entire sentence was negative. And so we basically don't give the model any indication of what causes this sentence to be negative. We're just kind of confusing it with a lot of weird training data that doesn't play into there actually being syntactic information. It's like saying I want to do parsing, but I just tell you this is a sentence, and this whole thing is a noun phrase. I don't tell you any more details about that sentence. And basically, what we're saying is I think we hit an upper bound in terms of accuracy of what we can do with that kind of annotation scheme, where we just have sort of a bag of words annotation scheme. We're just saying this whole thing is negative. And obviously, intelligent text understanding cannot be achieved with just bag of words representations or these kinds of global labels. And so what we propose is instead to see this as a structured prediction problem. And in order to really use that and train the model as a structured prediction problem, we basically needed a new suitable data set for training and also evaluating at what point in the composition are we actually capturing, oh, now there's a nod, now the sentiment changes significantly. And so basically what we did is we went ahead to Amazon Mechanical Turk and we gave people all the phrases of these different sentences. And so here we have the sentence is not life-affirming, it's vulgar and mean. So these are all very negative things. Life-affirming by itself is positive, but we immediately see, okay, not life-affirming is negative, and so on. And then we have the but here, and it already gets slightly less negative because you kind of realize something might be coming, and then you realize, okay, what came after the but, that's actually positive. So now this is the kind of training data that would actually help us to train for these kinds of effects if the model is powerful enough to capture that. So we collected a bunch of these, basically from 11,000 or so sentences. We have now 215,000 labels from Amazon Mechanical Turk. We showed people, of course, not the parse trees because you don't want to confuse Turkers with showing the parse trees, but we just showed them random phrases. And that's also important that they don't see the whole sentence and then have to label the subphrases because people don't necessarily understand that if I have certain subphrases that by themselves that are very different in sentiment, you shouldn't label them with the global label. So we showed them these phrases, and then we basically looked at some statistics. And the first thing we noticed is, okay, there are actually a lot of neutral words and very short n-grams. So here you see n-gram length, and basically, up until 10 or 15, you have lots of neutral. And we also see that very few people, we originally had sort of a continuous score like from 1 to 25, but really we capture most of the variance of this data by classifying it into 5 different categories: very negative, negative, neutral, positive, and very positive. All right, so with that, I'll go into the details later, but basically, when you add more data to the problem, everything works better. It's kind of a known story, and basically all the models improve by 2 or 3%. By adding this, additional training data. So that's great. However, a more in-depth analysis then showed us that the hard negation cases are still almost all incorrect. And we can create a data set where we simply change one word in the sentence. Now it's very obvious to every reader that that sentence became negative, and the models are still failing on it. And so that led us to basically also developing a more powerful model. And that's what I'll talk about next, which is the recursive neural tensor network. Again, the goal will be similar. We want to compose 2 vectors, but we basically want to have a more expressive composition function, and we want to allow both additive and what I call mediated multiplicative interactions of these vectors. So I'll describe to you down here how we basically combine the first pair of words, and then it's basically recursively again repeated in a similar fashion. So we have here a vector for very and a vector for good, B and C, respectively. What we first do is we concatenate them, and then we have this bilinear form here, where we basically get a single number out of this. Of course, we want to have multiple numbers such that the parent vector representation has again the same number of dimensions as each of the children vectors. So if everything is 2-dimensional, this thing would only give us 1 number, but we would want 2. And if in general it's n-dimensional, we want to have n of these multiplicative bilinear forms. And so what we do is we have basically several slices of then a tensor. And each slice basically will give us 1 number for one of the hidden units of the resulting parent vector. And then we add the normal recursive neural network also. We cross-validate it, and it still helps a little bit to also have that added. And then we add element-wise nonlinearity again to the resulting sum. So this now is a really powerful model that allows sort of different interactions. You can kind of see each of these, you can multiply it, and then each of these is like one hyperplane in the space, and that can capture sort of one way of these 2 word vectors to interact. And we again train, on top of this parent vector, we have a logistic regression, and we can take gradients with respect to both the logistic regression and all those parameters in here, and sort of train this whole thing in a backpropagation style standard neural network way. All right, so how does this actually work on a real sentence? So here we have, these are actually predictions of the model, but the word vectors are just kind of to visualize that we started. We actually initialized the word vectors randomly here too for this model, and they are just trained as part of the model. So we have not bad, not slightly negative, bad, very negative, and pretty by itself is sort of in its majority sense seen as beautiful, very positive also, and smart actually. So that was one of the phrases of the test set. And so we piped both of these vectors into the RNN, and now we get this nice effect that not bad actually becomes neutral, which is kind of intuitive. It's slightly positive maybe, but mostly even though you combine 2 negative things, you get something that is more positive overall. What's also interesting is, pretty by itself is very positive, so it was smart, but together you actually realize that pretty became sort of an attenuator, like, sort of, and together they're only mildly positive. And then again, we can use the vector representations that we have here, and we can pipe that into the same recursive neural tensor network. And because the tensor is a much more powerful composition function, we actually can get away with having the same one at every node of the tree, so there's no syntactic untying as we did in the parsing. And that's also one of the reasons why it's recursive, right? Because the output of the same model becomes the input to that model. And we can basically build up the tree in this bottom-up fashion until we have the overall sentiment of the sentence. And so once we have this new powerful model, it turns out that this is really the model that can make the most use out of this kind of data. It's the only one that really pushes the state of the art. And so now what used to be in the last 7 years below 80%, we basically pushed with this new data set and a new model that we have made use of that data to 85.4. We can look at also not just the final sentence classification that previous people did, but we can look at the fine-grained. Also, this number is only binary, so positive and negative. But we can look at 5-class classification across all the different nodes in the tree, and we can basically see here that the RNTN is much more accurate, especially compared to the baselines on sort of looking at the accuracy across all the different n-gram lengths, and it almost upper bounds all the other models at the different n-gram lengths. What's more interesting is we can actually look at some of the details in these hard cases that we found in the data set. So here we look at all the x but y sentences, of which there are 131 cases in the data set, and this is one of the outputs. It's really beautiful how it captures, okay, there's slow and repetitive parts, it's negative, but it has just enough spice to keep it interesting, now dominates. So it learned that somewhere hidden in this vector representation now, you're going to be dominated by what comes next in the composition. And so the RNTN is much more accurate, especially compared to simpler baselines, but also to the MVRNN, which actually has like an order of magnitude more parameters because of all the matrices that you have for every word and so on. We can also look at negation, and those will be the last set of experiments before I'll end. Here we have Roger Dodger as one of the most compelling variations on this theme. And for these negation results, we basically created a special test set where we try to change the sentence as little as possible in order to change and flip its sentiment. So here we have basically just changed a single word, most compelling to least compelling. And the model really nicely realizes, okay, now this least compelling actually, least is one of the ways you can negate compelling, and it becomes negative. Another one, nice example, I liked every single minute of this film. I didn't like a single minute of this film. And again, like a single minute of this film by itself is actually kind of interesting because like can be, sort of used similar to is similar to. So this is like something else. So by itself, it's more neutral, but once you didn't like something, it realizes that this is overall negative. So let's look at the actual numbers here for negation. So first, what we looked at is when we negate positive sentences by a very minor change. And this is when really the RNTN beats all the other models on these really hard cases, and it's like almost 20% more accurate than the next best recursive neural network type model, and an incredible amount more accurate than the simple bigram naive Bayes, which had actually beaten all the previous methods, all the nice dependency parse models and conditional random fields and dependency parses. If you actually carefully tune your bigram naive Bayes, that was the best model that came out before. So this is actually a relatively strong baseline. So what we can see is when we look at the classification, and we have these 5 classes, we can look at how much, once you negate something at that node, how much do the activations of the multinomial change in the predictions? So, I have very negative, negative, and neutral, and I want to see how much more negative do things become? How much more probability mass do we assign to the very negative and negative classes? And we can basically see that the RNTN is able to make things much more negative. But in general, all these models capture the main fact that once you negate almost anything, it becomes more negative. So then we're kind of worried, well, what if our super fancy RNTN, all it learned is you see not, you just really pound it and you make it very negative. So then we looked at what happens when you negate negative sentences. So we know that when we negate positives, everything gets more negative. But when you negate negatives, it's actually a little more complex. You don't just have a flip. So if I say, not bad, it doesn't logically flip, like I said before, to very positive. But things do become less negative. And if we have here the example, it's just incredibly dull versus it's definitely not dull. Something being not dull doesn't mean it was super exciting and entertaining, but it definitely means that it wasn't as boring as just being dull. And these are basically the distributions of the activations that we can see when you have not and you combine it with bad. Bad is incredibly negative, not is somewhat negative, and together actually they become neutral with a slight, off balance, slightly more probability mass on the positive ones. So looking at the numbers, this is where the RNN really showed that it can capture much more than all these other models. Basically, the accuracy for negating negatives for the RNN was 81.8, and the next best model was way, way further down. And that is basically because when you look at that node where you have some negative phrase, then you add the negation, at those nodes, the RNN is the only one that actually was able to increase the positive activations. None of the other models that we trained was actually able to capture that effect that, there's really, once you add negation to something negative, it becomes more positive. All right, with that, I want to try to play around with the demo that we built for this. The demo is always a little bit scary because Murphy's Law will tell you that we'll find a way to break it, but it actually works often enough that I hope we'll have some fun examples. So here, you can basically give any sentence that you want. You can play around with it also under nlp.stanford.edu/sentiment. And so this is one of the examples I had mentioned before. Here we have, this movie doesn't care about cleverness, wit, or any other kind of intelligent humor. These are all positive. It's again kind of sad that intelligent by itself is not as positive as just humor, and intelligent humor not as intelligent as humor itself. But so here you basically see that once you have the doesn't, and the care here, this is actually a slight mistake, so this should have been positive also. You see kind of in the distribution that it has much more weight on the positive classes. But the main thing is once you have the doesn't here in front of it, then it realizes it becomes negative. And so does anybody have a sentence that we want to try for the demo?
I wanted a sentence with two negations.
All right.
But I cannot come out.
It didn't not impress me.
Okay. It's a little contrived. I don't know if it's similar to what we would see in the training data, but yeah, it did not get that right. So to not impress you is pretty negative, and to didn't not impress you is also very negative. Yep. Well, there you go. So you maybe shouldn't do it in an online demo, but so yeah, we actually have it's kind of fun. So here are some of the failure cases. One is if you create something that's a little contrived. So also some people are like, it's not bad. And then they're like, oh, but I counted that, it's 5 not, so now it should be positive, and it's a mistake. But the point is that nobody actually uses that language. Like, some of these are so contrived that yes, the data set has never seen something like that. Some other failure cases, maybe before we can go to another example, is some very world knowledge that you've never seen before. In some sense, you can actually see sentiment analysis as almost being NLP complete. So one person, so we actually allow people to comment on it and let them complain and vent their frustration when it doesn't work and so on. But one thing was this movie was like getting your eyes poked out with a rusty needle. It's obviously it's very negative, but the model doesn't have eyes, it can't really see, understand that that's a bad thing. It's never seen the word rusty before, so unseen words and vocabulary. But one sort of more important problem that you can have is when the parser messes up. So sometimes it puts the negation somewhere really low in the parse tree, and you can kind of see how it struggles to negate the positive things, but then if it wasn't high up enough in the parse tree, it won't work either. But okay, so let's try one or two more times until we find something that works. All right, we'll do.
Just to take out of this, it didn't fail to impress me.
It didn't.
That's probably a skill.
Yeah, it's somewhat similar to the one we just had. It's actually exactly what we just had. Wait, it didn't. Yeah. No, impress me. Failed to impress me. Yeah, but then.
It should be positive.
Yeah. Yeah. Yeah, it's kind of similar. It's actually very similar parsing to the one we just had.
Do you do fragments like yeah?
I don't know. I don't think so. This is trained on like people writing like reasonable English. I don't think it might not even know. So yeah, it's actually an unknown word. So like it doesn't do much.
I can't believe that this is not a worst movie.
All right, let's try something else. It's very similar to the one we just had. Which I mean, maybe we can try it later. But yeah.
I would only recommend it to my worst enemy.
So this is actually where I would only recommend it to my worst enemy. So this is actually a nice example of like also world knowledge, sort of recommending something to somebody you don't like. So
The worst.
Worst.
Actually got it. So yeah, so I guess worse is something that actually gets this right. So this is negative. One thing that's kind of nice. So I guess it doesn't work. Maybe we should end right where it worked. But one of the nice things is in the examples where it doesn't work. So here didn't fail to impress me. What we actually like you to do when you find an example where it doesn't work. So it was right here, but then this one should have been positive. So you can actually click on this now and say this is positive, and so is this one. You can double click. And now you just helped us a lot by giving us some more training data, and you can now say all the remaining things of this tree are correct, and then we thank you, and with that we're actually able to, in hopefully next couple of iterations, use some more realistic language. Unfortunately, looking at the first couple of training examples that we get from that, there are also people who are kind of confused by the interface, or they create just really, really crazy sentences that I think will throw the model off more for standard English than it would help, but I think in general we hope to make use of this training data. All right, with that I want to conclude. Basically I hope I could show you that recursive neural network type models can learn compositional feature vectors for words and phrases. They can basically learn to capture some interesting linguistic effects, like subtle negation type effects, but also sort of soft notions of head words for parsing. We've gotten state-of-the-art for relation classification and sentiment analysis, and also a fast and accurate parser that is now the parser that we shipped at Stanford. And with that, I want to thank you. I don't know the time, but I guess we have some. Yep.
We've got a few minutes for questions. I'll start off by asking, so you talked a lot about compositionality, and you really convinced me that compositionality is an interesting, complicated problem. And you're getting a long way, but there's also non-compositionality in language, and it sort of seems hard to talk about compositionality without talking about the other one. And so, I mean, I can see a story that says, well, your composing operations are so powerful and so flexible that they're taking over that responsibility. Can you comment on, where you see this going?
That's a great question. So I guess the main question is like, how do you deal with non-compositional meaning of longer phrases? So for instance, to kick the bucket, it's just, it doesn't really make sense to see somebody kicking the bucket, because most native English speakers would know that to kick the bucket means to die. And so there are two answers. Well, the one main answer to that is if your composition function is powerful enough and it has actually seen certain phrases in that, roughly in that constellation, not exactly, but at least, he kicked the bucket, she may have kicked the bucket, or things like that. If you have enough neurons and enough sort of representational power, the composition function can actually just memorize certain expressions. And I think, especially like the tensor network type of model might have the ability to just memorize certain non-compositional.
So can you extract those expressions once the model is learned?
I mean, it's a very theoretical, because I haven't actually looked into those expressions.
In
but
principle,
I think you
look
could
into the model and see which things it's finding is not.
It's a little too hypothetical. My general inclination would be to say yes, because so far, basically everything I've tried with the RNNs, I got it to work eventually. But So in the simplest case, well, there's actually somebody in Adobe's group who's looking right now at using these kinds of models for trying to find sort of anomalies in events. So they have some correlation numbers at first, but maybe you can check with them. I think there are some ideas where you can sort of look at, how surprised are you in a certain node structure to see something, or you can just train a classifier for multi-word expressions. I guess people have like enough workshops now that there's probably a training data set for that you can throw in, at least like classify them. Yeah.
Thanks for the great talk. I want to ask something about fine-tuning the model. So for example, what's the differences using sigmoid as compared to tangent, and what are the differences using different ways of initializing the word vectors and matrices, and in choosing different sizes for the word vectors?
Great questions. All great questions. I guess we could talk for at least another 10-15 minutes about all the details, which I guess is actually true for every machine learning model out there, right? Like even for topic models, there are certain subtleties of like stop words and so on. I think on the high level, every decision that you have for your first one or two projects in this space, like I think pretty much every new machine learning technique you start working on, you should just cross-validate a lot. You have a nice train, def, and test split, and each of these decisions, if you're uncertain, just run it and let the model make the decision of what it should be. After you've done it a couple of times, which I have, you know that in these kinds of models, 10H works much better than sigmoid. I kind of attribute that to allowing for negative activations in the non-terminal nodes that can then interact with other possibly negative or positive vectors, whereas like once you run it through a sigmoid, everything will be positive, and you won't have certain as powerful sort of flips and negations in your composition. In terms of word vector size, that's usually a cross-validation parameter that we do every time. So we try 25, 50, and 100, and in almost all cases it's best at around 50 or like 25. Once you have more than 100, usually the data sets aren't big enough to gain anything from that, and you start to slightly like overfit some more and generalize less well. And in terms of word vectors, there's actually a lot of interesting work on word vectors. It turns out that for parsing, for instance, the word vectors are incredibly useful. I didn't talk about this because I think Chris did, but if you have a sense like he eats spaghetti with meat, if you now have other things like meatballs or pasta, or, veggies and so on, you kind of know that they're all in the food category, and then you can learn that, all right, with something food vector, the PP attachment here would attach to spaghetti and not to the eating. So if I was to say like he eats spaghetti with the fork, then with the fork should attach up here, and you can make certain assumptions, like certain inferences from very few training examples when you have these distributional vector representations. And so for parsing, it's incredibly useful to have these unsupervised learned word vectors. However, for sentiment, in this case, all these experiments, we actually had a large enough training data set, at least to push the state of the art back quite a bit. Data sets can never really be too large, especially not for powerful composition functions and general like nonlinear kinds of neural network models. But we had enough training data that we didn't need to pre-train the word vectors at all. We just randomly initialized the word vectors, and then there's sort of a very simple sort of mathematical underlying sort of, I don't quite want to call it theory, but the main point is how do you initialize your word vectors and basically any kind of vectors and weights in neural networks. And the thing you need to understand is you have these nonlinearities, right? Say you have 10H, and when you initialize your weights such that you have like the values of like 10 or 15, you kind of know that once you get an activation in your first sort of forward pass that maxes out at one of your units, your gradient is close to 0. So you just never want to initialize your weights to very large values, because otherwise you just you get stuck in the local optimum right away and nothing happens. So as long as you initialize your weights such that you're roughly in sort of the slightly linear regime of your nonlinearity, then you're usually okay, and that's just small numbers between like uniform between -0.001 or something, and then you're good. I think those are sort of the most important general.
So when I was first seeing this sort of things in the last couple of years, it made my head hurt to try to think about how this could relate to like traditional logical semantics. And the thing that I think makes sense actually is to think of it as a hash function for semantics, where you're mapping more complex things into a fixed size vector that's like kind of the right thing to compare. Does that make sense?
Yeah, so I actually have some results on logic too. So the MBRNet, for instance, can perfectly learn like propositional logic. It's not that hard. You just give it a bunch, like the 6 training examples of or and nots, and then it will just, with a specific type of nonlinearity that will give you back a perfect 0 or 1, you can learn sort of simple propositional logic. What's more interesting is you can actually also almost reason over sets. We have a NIPS paper last year where we basically do knowledge-based completion, where we have a neural network architecture that actually is exactly the neural tensor network that I described here, but only with 2 entities each time. So like dogs gets thrown into the has part neural network with the vector of tail. And then you train that dogs and tails when given as input to a neural network that tries to capture the has part relationship should get a high score, a large probability. And like a car has part tail should get a low probability. You can from WordNet or other knowledge bases you can create a bunch of facts like that. And then you train the model, and what's amazing is you can then actually do like very transitive inferences where you said, well, I know that dogs are similar to cats, and I know that tigers are special subcategory of cats, and I know that Bengal tigers are special types of tigers, and now I tell you dogs have tails. What's amazing is it actually is able through these vectors to sort of capture that eventually Bengal tigers will probably also have tails. So there's some interesting sort of semi-logical reasoning. That's actually one of the things I'm looking into right now, sort of how to ground meaning in both knowledge and facts, and also the visual world. To sort of connect those. I have one question.
So that leads to my question. I see. There's no reason that the aspects of semantics that you're combining should be limited to sentences. Have you done any work going across sentences?
That's a great question. That's actually also one of the things in my research statement that I'm mentioning that I want to do in the next couple of years. I have not, but I have some very concrete ideas that I'd love to explore. Basically, you could try to, there are multiple things. So the simplest one is you could have a recurrent neural network that just sort of kind of connects sentences at one level. You can also try to do sort of discourse parsing, dialogue parsing, where you say as multiple sentences, and some sentences are more similar or more important to be connected to each other, and you kind of have like a dialogue parse and have just another recursive neural network on top of the sentence structures. And then, of course, the question is always like, what are you at some point capturing when you have 50 or 100 words in one vector? And of course, you're not asking the vector to memorize everything that it's seen, but sort of to capture the gist. And the higher up you go, the sort of more abstract your representation should be, up until saying like, all right, it's kind of like topic models, right? You don't expect the topic models to be exactly, knowing what all the words were in the document, but you just kind of want to get the gist of the document at that point. So yeah, I think it's very interesting future important.
Scalability. Any comments?
Sure. So for these, one of our larger data sets with the 12,000 sentences and 200 something thousand labels inside, the model trains in about 4 to 5 hours. In fact, basically all the models that I described to you train in about 4 to 5 hours on a single cluster machine, single server. One of the things that used to take an incredible amount of time was to learn these word vectors, but we have some things in the pipeline where we can learn those in like an hour and a half.
But I remember in your paper you mentioned about using low rank.
Using low rank?
Using low rank matrix to reduce the computational cost. So I like to say more.
So the low rank, of course, helps a lot, both in terms of less overfitting, and also in terms of speed for forward propagation in the MBRNet, and of course in the